In this section, we'll talk about optimization error and sampling error in fitted queue iteration. Just to recall what fitted queue iteration means, fitted queue iteration is an algorithm that trains a queue function by running a sequence of Bellman backups that minimize the mean squared temporal difference error. So you start from an initial queue value q naught, and you obtain each successive queue function iterate qk plus 1 by solving a least squares problem or a minimization problem that tries to find a queue that most closely matches the Bellman backup operator t hat applied to the previous queue function iterate qk. And this minimization happens with the square difference under the 2 norm, means that you're trying to just compute this q minus t hat qk squared for all state action pairs, and you're summing them over. So this is what FQI does. Now, one point to note here is that if we use the actual Bellman operator t, which is the exact Bellman operator, instead of the sampled Bellman operator t hat, which is being used here. So sampled meaning that the reward function and the next state or the dynamics function are both samples. If you use this operator, if you use the actual operator or the t operator, and let's say for a moment that that qk plus 1 was exactly equal to tqk on all state action pairs, then we can argue that fqi converges to the optimal q function q star, because what we are really doing is we are doing value iteration or q iteration. We are applying the Bellman operator over and over onto the q function. So what are really the sources of error that then we are considering then? Because we are for sure considering some sources of error. So what are those? So there are two sources of error here. The first source of error is that the notion of the Bellman operator, which is t or t hat, that's inexact, because t hat consists of sampling error due to limited samples. The same way as the generative model, p hat consisted of sampling error because it was not equal to p, and you were observing samples and constructed this empirical model. T hat here is also empirical, so it consists of sampling error. Moreover, even if you assume t hat were equal to t, the Bellman error that you observe in this expression, which is qk plus 1 minus tqk, it may not be equal to 0. And why will it not be equal to 0? It may not be equal to 0 because of, let's say, some error that you incurred because of a function approximation, or error that you incurred because you could not minimize this term exactly. So due to those errors, these things would be non-zero. And both of these quantities contribute to the overall error, because t being inexact contributes you to minimizing the wrong objective or an incorrect objective or a slightly biased objective, and the fact that the Bellman error is non-zero tells you that you could not optimize that objective, and hence you are paying a price. And just to recall before we start the derivation, t hat q is equal to the empirical reward plus the empirical next state's value, where the maximum value at next states drawn from the empirical distribution, which is s prime drawn from p hat, which you can think of it as, again, the generative model distribution from before. A small point here, which is that the reward function r hat, you can assume it to be equal to r, even if you don't assume that. We'll get some error due to that reward, but it will not be like a major game-changing factor in here. Okay, so now let's go into our analysis. So the first step, as we did for the generative model stuff, we'll bound the difference between the empirical backup and the actual backup. So back then, in the generative model setting, we bounded the difference between p hat and p, which is the actual dynamics model, and the empirical dynamics model. Here we'll do the same thing, but here, since we're not directly using the dynamics model, but we're using the Bellman backup operator, we'll talk about the difference between the Bellman backup operators. So what we'll do is we'll bound t hat and t, or t hat applied to q and t applied to q. Now, just by substituting the expressions for t hat and t, we observe that this difference can be written as, or the absolute value of this difference can be written as the absolute value of r hat minus r, and gamma times the expectation under the expectation under the empirical dynamics model p hat, and the expectation under the true dynamics model p of the maximum q value at the next state. Now, how can we bound this? So if you look at these terms, so let's first of all think about what's a high-level strategy we would follow, and then let's do the math. So if you see r hat minus r, and let's say r hat is estimated by averaging over different measurements of the reward function that you saw when you sampled SNA through your MDP, what it really corresponds to is sort of a concentration of the reward function, because r hat is the empirical expectation or the sample mean R is the true reward function. The sample mean converges to the true reward function at a certain probability. So that's really concentration of reward. Similarly, the other expression which is marked in blue is the concentration of dynamics. So it's not really a bound on p hat minus p, but if you look at what it's really, if you look at it more carefully, it's really saying that you are summing over some value which is max over a prime of q s prime a prime, depending upon probability p hat of s prime given sa or p of s prime given sa, and you're taking the difference. So in a sense, it basically is something that depends on the difference between p hat and p. So if p hat were equal to p, this would be 0. And so this thing also somehow relates to the concentration of the dynamics model. So really what you see here is two independent blocks in this expression that both depend on concentration. So how can we go about it? So the first step, I would argue, is apply triangle inequality. So we know we have seen techniques to bound we have seen concentration techniques to independently bound random variables. We can independently talk about how far away the sample mean of R can be from R, or sample mean R hat can be from R. We've talked about how far away the dynamics model P hat can be from P. But we've not talked about how we can do them together. But we know of this mathematical tool, which is the triangle inequality, to break these two terms into their individual absolute values separately. So that's the first step. And now this is interesting because now we can simply apply, or we can utilize bounds from before and directly apply the triangle or directly apply concentration results on these terms individually. So the first part, which is the reward function, it's the most straightforward part because we see that if you imagine R hat is the mean of different reward measurements RSA at a state action pair SA, we can directly apply the Heffding's inequality. So we can say that with high probability 1 minus delta or more than 1 minus delta, we find that R hat SA minus RSA is lesser than the maximum or the bound on the reward, which is 2 times R max, because we assume the rewards are between negative R max and R max, times square root of log over 1 over delta, which comes in because we are talking about a high probability guarantee, divided by the number of samples, or twice the number of samples m that you queried the reward function for at s comma a. So that's sort of a bound or a high probability upper bound on R hat minus R. For the second term now, that's somewhat more complicated. But let's write it in this somewhat different form, which instead of having expectations, writes it in the form of summations. So the expectation is essentially the sum over. So this is all assuming that S, A, S prime are discrete random variables. So you can sum over the probability P hat of S prime given SA times the max over A prime Q S prime A prime, and you can do the same thing for the second term where you sum over P of S prime given SA. Now, because max over A prime of Q S prime A prime is a common term, you can group the P hat minus P and bring that in the center, multiply that by max over A prime of Q S prime A prime. And still the absolute value still holds outside because all the transformation we have done so far is is inside of this absolute value. Now, if you write this in vector form, we would obtain something that looks like that resembles a lot like P hat minus P times a value function from the generative model derivation. So if the last but one inequality or the last inequality on this slide is written in vector form, you would find P hat minus P times some quantity that depends upon the Q function, and the norm of that, because that's really what this quantity looks like in a vector sense. And we know from the generative model derivation that we could bound this quantity by using the maximum L1 norm of P hat minus P times the infinity norm of the Q function. So Q infinity, which means the maximum over A prime and S prime of the Q function. And finally, basically what we are doing here is we are saying sum of product is less than sum of absolute values in a sense. I mean, not quite, because we are talking about norms for the distributions and P is a matrix, but basically the intuition is exactly this. And the Q values, they're bounded by the infinity norm here. So if this is unclear, you should revisit the generative model derivation where we essentially went through this step by step because it used the same or a very similar term where we had p hat minus p times the value function, and we were trying to bound that, and we bounded that by the maximum possible L1 divergence in the dynamics function. So p hat minus p, L1 norm at maximum over s comma a, and we multiplied that by the maximum or the infinity norm of the value function. And here that turns out to be the Q function. Okay, so now that we have bounded both of these terms individually, how does the overall bound on t hat q minus tq look like? So we'll combine the bounds on the previous slide, and also remember that so far what we've done is we have bounded t hat q sa against tq sa. So this is for a particular state action pair. But what we really want is we want a bound that uniformly applies on all state action pairs. That is, it's a bound on the infinity norm of t hat q minus tq. So we want to take a max over all state action pairs of this bound to be able to say something. So it turns out that with a little bit of algebra, the bound on t hat q minus tq is less than or equal to the individual sums, except that you will introduce two constants c1 and c2 here, which will account for the fact that you are taking a max over all state action pairs. Meaning that this result from before was valid for a state action pair SA with high probability 1 minus delta, because both of these things were applied with high probability 1 minus delta. But when you take it over a max over all state action pairs, you're really asking for this probability 1 minus delta to hold true together for all state action pairs in your MDP, right? It's supposed to hold true for all of them. So there's so basically what we need to do is we need to kind of if you want a high probability guarantee, which is still 1 minus delta for all the states, we need to account for like a constant multiplier in the bound that comes in because of this reason. And because of the same reason, you observe the mod s, mod a, and mod s terms come in the expressions as well. So in the most general setting, basically, this is not really the most important bit here, but we need to take this, because we are taking this bound over all state action pairs, we need to invoke this union bound principle, which says we need to basically have high enough probability over all state action pairs together at once, and so we get a larger bound. So we cannot anymore guarantee that the reward function will be bounded by log 1 over delta, but we'll get a log SA over delta in there, as you see on the slide. We can go into more detail about this in our in the lecture as to how exactly this bound comes in, but this is a standard thing in statistics or concentration inequalities. So once we have this, what we have done so far is we have bounded t hat q against tq. Now, how does so if you want to use this for explaining how the resulting q function out of fqi is different from the actual q function q that you would expect, then we need to talk about how exactly the fitting error in each iteration, which means how exactly the Bellman or the TD error that you train your q function with in each iteration affects optimality, affects your q function at the end. So let's say that we incur, and this is the step which we'll go into now. So let's say we incur epsilon k error in each fitting step of fqi. And for now, for the second step, for a moment, let's assume we had the true Bellman operator. So that our derivations are somewhat simple, and at the end we'll combine the two. So let's assume that step 1 is done, and let's keep it at the back of our minds. And now let's assume that we had the true Bellman operator T being used in the Bellman for the Bellman update, and not the sampled operator. Then let's say that we incur error epsilon k in each fitting step of fqi, which means that the infinity norm of qk plus 1 minus tqk is less than epsilon k. And epsilon k could be due to some reasons like function approximation, maybe because you're doing gradient descent rather than exact minimization, something of that form. Let's say this is the case. Then can we say something about qk minus q star, which is the end goal of fqi, if you had epsilon k equals 0. So if you actually did fqi, which means you actually did q iteration with 0 error, then you would hope to converge to q star, but here you may not converge to q star. So what is the difference between qk minus q star? Again, in an infinite norm sense, we want to answer this. So now what we'll cover next is basically sort of a nice a recurrence relation, which you can utilize to analyze such bounds. And it's a general purpose trick that has been used in the past to understand Q functions of all sorts, because Q functions have this nice recursive relation, and that we'll cover next. So this part which we'll cover next is sort of independent interest outside of this proof as well. So qk minus q star infinity, what we'll do now is we know that qk is basically obtained by from t qk minus 1, right? Because we are minimizing Bellman error against t times the qk minus 1, which is the Bellman error, which is the Bellman targets from the past iterate. So what we'll do now is we'll use, and we also know the fact that q star is the optimal Q function, and it's the fixed point of the Bellman operator. So Q star is equal to T applied to Q star. So Q star is TQ star. So what we can do now is we can utilize these two facts to do a little clever trick here, where we add and subtract TQK minus 1 from this expression. So from the expression inside of the infinity norm, we'll add TQK minus 1 and we'll subtract TQK minus 1, as you see on the slide. Now what you see is you can group together QK and QK and negative TQK minus 1 together, because that's something you control, that's something you optimize, that's the TD error that you are optimizing. And for the other two terms, if you see, those are terms that basically apply the Bellman optimality operator on qk minus 1 and q star, because basically they apply them together. So, and you can bring them together as well. Now we know that the Bellman before that, so we know that the absolute value of a sum of vectors, or the norm of a sum of vectors by triangle inequality is less than the norm of individual of those vectors. So you can use triangle inequality here, and you can break this summation down into two terms, where the first term now is tqk minus 1 minus tq star, which is this additional thing that we introduced, and qk minus tqk minus 1 is the TD error, or the Bellman error, that we knew something about from our assumption, or from the fact that we incur epsilon k error. Now what we'll do next is we'll utilize the fact that t qk minus or the Bellman operator t is a gamma contraction. So this is something that you looked at in the very beginning, and it's covered in any other RL course, where like CS188, if you have taken that, where we show that the Bellman operator is a gamma contraction. So you can utilize this fact to say that tqk minus 1 minus tq star is less than or equal to gamma times qk minus 1 minus q star. And wherever the subscript infinity is missing, we are everywhere talking about subscript infinity. So we are everywhere talking about L infinity now. And what I can do also is I can replace qk minus tqk minus 1 by its upper bound, which is epsilon k, which is my assumption for the fitting error. So what I get now is I get a recurrence relation that says that the infinity norm between qk and q star at the kth iteration is bounded by gamma times the infinity norm at the k minus 1th iteration plus the instantaneous Bellman error epsilon k. Okay, so how can we utilize this relation that we saw? What we can do is we can unroll this recurrence one more step. So we say, okay, I'll do this. I'll use the same sort of error analysis, same sort of recurrence decomposition for qk minus 1 and q star, and express that as qk minus 2 minus q star. And in that process, what I'll do is I'll obtain a gamma epsilon k minus 1, which is from the last iteration, and I'll get a gamma square multiplier on the infinity norm. I can do this k times, where I would end up obtaining q naught minus q star multiplied by gamma to the k, plus a summation over gamma i's multiplied to the errors and to the Bellman errors. And note that here you are basically sort of multiplying or like the later, or the earlier in the chain, or the earlier in the Bellman sequence of updates you saw an error, you are discounting that more heavily, because it has been more iterations still since then that you reached k. So it's gamma to the j times epsilon k minus j because of this reason. Now, what is this gamma to the j epsilon k minus j? If you think about it, intuitively what it means is that if you incurred, or if you paid a price of, let's say, epsilon 1, epsilon 2, epsilon 3, so on in your previous iterations, you're essentially still kind of retaining the error due to the error that you made there in your actual expression for qk minus q star. Because unlike supervised learning here, what's really happening is that because you're reusing target values, or you generating target values from your previous iterates, you're really paying a price for whenever those target values were wrong, or whenever those target values could not fit their corresponding Bellman error targets. So in a sense, what is really happening is that error compounds or error propagates here, meaning that whatever thing you did in the early iterations, those will follow you along until the end solution. The first so let's consider a large number of fitting iterations here. So let's consider k is like super large. Then the first term essentially is just not useful because you are discounting q naught minus q star, which is a constant because q naught is your initialization and that's up to you to choose. You're multiplying that with a number less than 1, which is, or gamma, which is less than 1, to the power of a large k value, which is kind of going to be small because we know any number less than 1 to raise to the power infinity tends towards 0. So that term is really 0. You can kind of just ignore it for now. So the real term that comes up in this error, or qk minus q star in the infinity norm, is the sum of this accumulated Bellman errors or accumulated TD errors, where by accumulated I mean the special multiplication over gamma to the j's. So and what you can do now, just for the sake of mathematical simplicity, you can say that let me imagine that my error epsilon had an infinity norm, meaning that I know what the maximum error epsilon could be, let's say. Then what I can do is I can say that this summation is bounded by the sum over only gamma to the j's times the maximum allowable value for epsilon, which will give you, again using the geometric sum series formula, epsilon infinity norm divided by 1 minus gamma. So it's just saying that any Bellman error that you incurred, it's sort of magnified by a factor of the horizon, which is 1 over 1 minus gamma that you see here in the slide. So we pay a price for each error term, which is error compounding, and the worst case, you basically scale this error at each step by 1 over 1 minus gamma, which is essentially going to be large. Okay, so finally, what we have shown so far is we have shown how error in one step, or fitting error in one step, affects the error against q star. We have also discussed how sampling error in the Bellman operator affects how sampling error in the Bellman operator affects the value against affects the actual Bellman operator. So let's now put these together to get a final bound for fitted Q iteration algorithms, or final error bound for fitted Q iteration algorithms. So what you can do now is basically combine this optimization error and sampling error together. How will you do that? So note this essentially. So qk minus tqk minus 1, which is the Bellman error with the exact Bellman operator that you actually sort of require in the previous error bound. So the error bounds that we saw so far on qk against q star use the true Bellman operator t here. So this infinity norm, which is the quantity that appears as the epsilon in the optimization error, this is really equal to by adding or subtracting or adding and subtracting t hat qk minus 1, you can say that it's equal to sort of a sum over, or it's in the worst case bounded by the infinity norm of two quantities, or the sum over infinity norm of two quantities. The first quantity is the empirical Bellman error, which is the Bellman error that you are actually minimizing in your algorithm because you are training against t hat qk minus 1. And the second term is how different t hat qk minus 1 is from tqk minus 1. So that's the sampling error bit. And the first bit is what you control already. So if you guarantee that this bit is less than some threshold epsilon or whatever, you control this guy. The second term, it really depends on how many samples you have seen for SNA, but we proved bounds for this in the first part of this proof. And finally, what you need to do to get the overall error bound is take qk minus q star and use the fact that you are you're upper bounding this by 1 over 1 minus gamma times the maximum Bellman error, which you know is upper bounded by the sum of these two optimization and sampling error terms that we derived so far. So essentially, you get the overall bound that says qk minus q star in infinity norm depends on some term that depends on sampling error and the optimization error, which is controlled by how easily you can minimize your empirical Bellman error in the algorithm. So what's the proof takeaways? I'm leaving the final expression for you to figure out, but essentially it's just taking over the bound on t hat q minus tq from before, putting this in here. An optimization error is something you control, so you know how large its value could be. It could be as large as, let's say, some assumed value delta k or epsilon k, and you can just feed it in here, and that's your final part. So what's the takeaways from these proofs? So we saw that a lot of abstract quantities were introduced, like we talked about epsilon, we talked about t hat q and tq and so on. But what does this proof intuitively tell us? And that's what we'll discuss now. So intuitively, first of all, it tells us that error compounds with FQI or DQN style methods, which means that if you paid a price at a local step, at a local optimization step, meaning that the Bellman error, which is this quantity qk minus t qk minus 1, if that quantity is high, which means that either the optimization is bad, which means you cannot minimize the true Bellman error, or sorry, if you cannot minimize the empirical Bellman error that your algorithm is training with, or if you have high sampling error, which means that you have seen certain state action pairs only a few times. If that's the case, then the actual Bellman error is high, and because of this actual Bellman error being high, you will pay a price due to the error compounding, because you are using this and you're multiplying this by 1 over 1 minus gamma. And note that this is especially a problem in offline RL settings, where this notion of sampling error can be extremely high. For instance, if you haven't seen a particular state action pair in your data set, if you recall what this expression for sampling error looks like, this expression depends on the number of times you've seen SA pair, which is m in the expression in the first line. So if m is very small, you're going to pay a larger price there, and that larger price translates to a larger error in your Q function. So if you recall, this basically kind of connects back to the notion of how the Q function was erroneously estimated, like overestimated a lot in offline RL settings. Secondly, one other thing to note here is that these proofs typically require a stringent assumption. So what we have been bounding so far is we've been bounding the infinity norm of the error in the Q function. But if you ask yourself, if you consider the problems that we care about, which have a lot of states, can we ever really practically bound the error at the worst state action pair? The answer is probably no, because we don't know which state action pairs are really important, and we might not even have seen each state action pair in our data set in enough number of times. So we really care about sort of a distribution of state action pairs and not the worst state action pair. So the infinity norm notion is somewhat stringent. So can we remove this dependency on infinity norm? The answer turns out to be yes, that you can remove this dependency on infinity norm, where you consider sort of LP norms under data distributions mu. So what you do is you compute qk minus q star to the power p expectation under mu, and take the power 1 over p. And what you could do now is, if you compute something like this, you can still sort of retain the same style error analysis that we saw so far, but you may not be able to, or you'll get somewhat complicated expressions. So you'll get notions of how distributions shift with each other. So how mu is different from the distribution of states that Q would have, etc. And those density ratio like terms will come in, like mu SA by the distribution of states visited by the policy computed from QK. And those things will come up. So the expression will be complicated, but you can do similar analysis there. And if you want to look at this, there's a lot of work on LP norm bounds for Q functions, and that could be something interesting. Okay, so that broadly ends the second module of the course. So what's the third part that we'll look at? So far we have looked at sort of the generative model setting, or the Bellman error setting, the fitted Q iteration setting, where you in a sense had Oracle MDP access, in that you could basically compute an approximate dynamics model, and you assume that you already had samples given to you. So even in this fitted Q iteration analysis, we assume that t hat concentrates to t, which means that we assume that we can compute t hat, or we can compute t hat to a reasonably good degree of accuracy as t. But what happens when you are supposed to collect your own data, where you don't have access to such a dynamics model, but you need to have your exploration method go to states and collect your own data? So there, this notion of m, which we have assumed so far almost constantly that we can have that many samples, is sort of also becomes a complicated notion, because now m is supposed to be collected by your own policy from the previous iterate from your algorithm. So how does that work out? That's coming up in the next module.